Hello everyone, and welcome to AISC's Night School, Seismic Design in Steel, Concepts and Examples, presented by Raphael Sabelli of Walter P. Moore. Today is February 12th, 2018, and this is Session 2, Seismic Design of Moment Frames. My name is Brent Liu. I am with AISC's Continuing Education Group, and I'll be moderating today's presentation. So let's get started then. I want to introduce tonight's speaker, Raphael Sabelli. Raphael Sabelli is the Director of Seismic Design with the San Francisco office of Walter P. Moore Engineers and Consultants. Mr. Sabelli has recognized expertise in seismic design in steel structures. His experience includes the design of new structures, retrofit of existing buildings, nonlinear seismic analysis, and the development of new structural systems. He participates in several national committees responsible for building code development, including several committees here at AISC. Raphael is the author of the entire course for this night school, and as such, he will be the speaker for all 8 sessions. And so without further ado, please welcome back Mr. Sabelli. Raphael, thanks for being here, and I'll hand it over to you.
Thank you, Brent, and welcome back, everybody. So let's continue. I'm glad we got through last week's session. Despite my cold and coughing, this week things should be quite a bit smoother. We reviewed the course objectives last week. I won't spend any more time on this than to say tonight's course on special moment frames fits into it, both showing the principles of seismic design and the application to this system. As always, I would direct you to the resources that we've identified for this class. I did draw on the facts for steel buildings, earthquakes, and seismic design in a couple of the answers to the questions that I received via email after last week's session, and that's a free download from AISC. Other resources include the AISC Solution Center and Night School. So we've started with introduction to seismic design. Tonight is special moment frames. We'll hit braced frames and buildings in general in the next few weeks. And then we'll get into the design itself. So everything that we're going to look at today in general terms for design of moment frames, we'll visit again in a design example in a few weeks. So tonight, Session 2, Seismic Design of Moment Frames. We will talk about the behavior of moment frames, the elastic behavior and some of the post-elastic behavior, how we analyze frames. We will look in detail at the beam-to-column connection, and we've learned a lot in the last 20 or so years after the Northridge earthquake. And so we'll be looking at those lessons in great detail. We'll look at how beam-to-column connections are made in the field. We'll review pre-qualified connections, and there are a few other topics that I hope we'll have time to touch on at the end of this course, at the class. So let's start with the moment frame behavior in general. Our lateral resistance, we have horizontal forces. Those horizontal forces have to be resisted through column shear. There are no braces. If you cut a horizontal section across, there we go. If you cut a horizontal section across any of the stories, that horizontal force has to be there in column shear. And of course, where there's shear, there's moment. And if the column develops moment, the beam has to develop moment. The column moment has to go somewhere. And it's not just a cantilever from the base. And of course, where there's moment, there's shear. So since the beam has moment, the beam has shear. And those beam shear forces accumulate in the end columns into overturning axial forces. So those are the forces that we are primarily concerned with, the analysis of the magnitude of those forces and proportioning. So we get yielding where we think we want it. Those are the themes of the seismic design of moment frames. So we'll start with the lateral forces which induce the column shear. There's really nowhere else for the lateral shear to go. So we have a shear diagram that looks like this. I have intentionally made the interior columns appear to have more shear than the exterior columns. That's generally the way these things work. So a little bit more of the shear in the interior columns, a little bit less in the exterior columns, but the exterior columns, of course, take the overturning. As I said, where there's shear, there's moment. This is a diagram of the moment distribution in the columns only. And the assumption here is that the inflection point is mid-height of every story. That's not a correct assumption, but it's a good way to understand the behavior of the moment frames, to understand that the moment reverses and that these columns go into double curvature, perhaps at each story. During the course of the earthquake, it's quite complex, and that inflection point moves up and down quite a bit. And occasionally, during the course of the earthquake, columns may go into single curvature and have a little more complicated behavior. But for purposes of design, this condition here, where columns are in double curvature and we have the greatest magnitude of column moment and reversing at the beam to column connection, that is what we focus on for design. So the columns have moment. As I said, if the columns have moment, the beams have moment too. So as that column moment reverses, there is a discontinuity in the column moment diagram. That discontinuity in moment has to go somewhere, and it goes to the beam end. And so the beams have moment diagrams that look something like this. This is just the seismic moment in the beam. The gravity moment will alter the shape of those triangular segments of the moment diagram, as we'll see later. But this is a good idealization. So the beam moment diagram has a discontinuity at the column. That moment goes to the column. The column moment has a diagram has a discontinuity at the beam. That moment goes to the beam. And of course, where there is moment, there is shear. And the beams have shear diagrams that look something like this. Perhaps they are equal, perhaps they are unequal. It depends on the baseband, the beam sizes, etc. And the shear accumulates into overturning moments, which are generally quite large at the end columns of the frame, and there may be some small overturning moment in interior columns if the beam shears are unequal. So that's a representation of how a frame might behave, and all of that has so far been based on these line diagrams, the center line of the column and the center line of the beam. Now, if we look at an actual frame, the column has some depth and the beam has some depth. So considering the column depth, the column depth here, the beam stops short of the column, and so the beam moment diagram doesn't go to the column center line, it goes to the end of the beam. And stopping short, the value of the moment where the beam actually exists is less than the value of the moment at the column center line. Similarly, the beam has a depth, which means this moment reversal in the column doesn't occur over 0 inches, it occurs over the depth of the beam, 21 inches, 24 inches, 30 inches. So that moment diagram, instead of having a horizontal instant reversal, has a reversal over the depth of the beam. And so it has this sort of shape. And that has a couple of implications, as we'll see. One is similar to the beam. The maximum moment of the column is less than the theoretical moment at the beam center line. It's the moment essentially at the top or bottom flange of the beam. The moment near the center line is close to 0. But also there's a zone here with a steep moment gradient, and we'll look at the implications of that in just a moment. So beam stop short of center lines, moment reversal of column at the connection, high moment gradient at that connection. So as we look at the shear, the centerline model looks like this. But when we take into account the depth of the beam, we see that the column shear is actually quite large within the depth of the beam. That is the so-called panel zone shear. So within the depth of the beam, the column has high shear in that connection region, and often the design of the connection has to adjust in order to address what this so-called panel zone shear. Okay, so that's the basic mechanics of the system of the frame. Let's review what we discussed last week, that we would like to encourage for the moment frames flexural hinging to occur in the beams rather than in the columns, so that we might form a mechanism that looks like this. And you can see each end of the beam is developing a flexural hinge, and the size of this dot indicates the degree of rotation. Of course, this is just a conceptual sketch. And then, as I mentioned before, you can't really form this mechanism unless you get some rotation at the column base. But for the most part, the way that we idealize the behavior and the way that we try to encourage, in the behavior that we try to encourage, is to have yielding occur in the beams and not in the columns. And there are a number of reasons for that. One is that the columns are resisting sometimes quite high axial forces. And this also has the benefit of discouraging story mechanisms. So if we encourage flexural yielding in the beams, we are, in so doing, discouraging flexural yielding in the columns. And for a story mechanism to form, it has to form by the formation of plastic hinge, top and bottom, at a story. Here it's shown at the bottom story, which is probably where we worry about it the most as the largest P delta effect, but it could happen at other stories as well. So by making the column stronger than the beam, we encourage the yielding of the beam before this mechanism can form, and so we prevent this story mechanism from happening. So this, on the left, you see a photograph of a reduced beam section connection test in the lab. It's been whitewashed, so the specimen has been painted with a fairly cheap white paint. That white paint bonds with the mill scale that's on the steel. When the steel yields, it goes through significant strain, and that mill scale tends to flake off, and with it the whitewash. So areas where you see gray, that's where we've had significant strain in the steel, and that's where the yielding has occurred. So in this connection, as we discussed last week, we are encouraging the plastic hinge to form away from the face of the column in this particular connection by taking 4 bites out of the flanges, top and bottom, left and right. And that makes a weak zone of the beam where the yielding occurs. So here we see that it has occurred, and the column doesn't have any flaking or not significant flaking, and it's remained elastic. And so we think that, excuse me, in so doing, we've discouraged the formation of a story mechanism. On the right, you see the idealization of a frame with plastic hinges forming left and right end of each beam and at the column bases. Now this photograph on the left is a column yielding. It's a beam that's much stronger than the column. I'll own up that this is not a moment frame test. This is a test of a braced frame. Nevertheless, it's a fairly rigid beam to column connection, and the beam is a lot stiffer and stronger than the column, and so the flexural yielding occurs in the column as this goes out to large drift. And this is something that we try to avoid, as I said, in part because of the large axial forces that can occur in columns, and also in part because the potential for forming story mechanisms, as is shown on the diagram on the right. So this would not be compliant with some of the rules that we have, at least for special moment frames, and it's behavior that we try to discourage. Also, this high shear region that we discussed before, the column can yield in shear, and there are potentially some issues with that behavior. One is that it's possible that story mechanisms could form. We're still getting that rotation in the column. Also, similar to flexural yielding in the column, we're a bit nervous about high axial forces in these column flanges, and the column flanges having to undergo significant kinking as the panel zone yields. Additionally, that kinking is right adjacent to the highly stressed beam to column flange weld. Even if we've pushed the plastic hinge away from the face of the column, we still have very high forces in these welds of the beam flange to column flange, and putting the column flange through significant bending strains there can create the opportunity for those welds to initiate a crack and then propagate that crack through the weld. So the provisions, as we'll see later, do allow a little bit of panel zone yielding, but in general, try to encourage the beam flexural yielding even over panel zone yielding. Okay, so our fuse is, again, the plastic hinge that can form in the beam at each end. That's a beam flexural plastic hinging. And so we want to proportion our structure so that can act as the fuse. Remember, a fuse only works if the structure is properly proportioned. If the fuse is stronger than the rest of the system, it may be very ductile, but something in the rest of the system is going to yield first. So proper proportioning is key. We size our beams so that we size our beams and columns so that our frame is stiff enough. Then we take the beam plastic moment capacity and derive the forces that correspond to that. For the beam itself, as we'll see, there's a shear that corresponds to the formation of these plastic hinges, and we make sure that the beam is governed by flexure rather than shear. There are other ways that we encourage flexural yielding in the beam as well. For special and intermediate moment frames both, we have minimum span to depth ratios. So you can't have a beam that's very deep compared to its span, and therefore you're probably in the flexural, you're definitely in the flexural yielding region rather than a beam that's so short it might yield in shear. Okay, so returning to this concept here, we are proportioning so that we get flexural yielding in the beam. So we start with the plastic hinge formation at each end of the beam and derive the beam shear forces, and we also derive a number of forces in the column. The column shear at that location we will derive from the beam shear, and I'll show you how. The column flexure, essentially, we're deriving from the beam flexure. The column axial force, essentially, we are with a little bit of imprecision. That column axial force does derive from the estimated proportioning of the beam. And then the column panel zone shear we explicitly calculate from that beam flexural capacity. Excuse me. All right, so let's start. Let's move on to the elastic analysis of the frame. the frames have different sources of flexibility. All of these sources of flexibility have to be considered. They don't necessarily all have to figure in your calculations. Most software will directly be able to directly address most, if not all, of these sources of flexibility, but in some cases the modeling effort is quite intense. So let's start by listing these sources of flexibility. Axial deformations of the columns. This is important for taller structures. For a two-story frame such as I've shown here, probably not very important. But if you're dealing with a 15 or 20-story building, obviously you want to be using an analysis that, that can account for the axial deformations of these columns. Very important, the flexural deformations of the beams in the columns. This is always the primary source of flexibility of a moment frame. Each of these members has a moment of inertia, and it's the EI over L that accounts for the stiffness of the frame beams and frame columns. So that has to be accounted for in virtually every analysis of a moment frame. There can be shear deformations in both the beams and the columns. Typically, these shear deformations are quite low, especially for typical story heights and for the span to depth limitations that we have for special and intermediate moment frames. So yes, there are shear deformations, but with a minimum span to depth ratio of 7 for a special moment frame, the corresponding shear in the beam won't be that large, and so the corresponding shear deformation won't be nearly as large as the flexural deformation. Most software will automatically account for those, or will have the capability of accounting for those shear deformations, but for many typical building proportions, the shear deformations are much, much smaller than the flexural deformations. Now the shear deformations at the connections may be significant. That's the panel zone shear that we talked about a few slides ago. That panel zone shear can be quite large, and it can cause stresses close to the yield stress of the column web, and that can lead to a lot of deformation that then translates to a lot of extra drift. Then there are some connections that in moving the plastic hinge away from the column face either weaken the beam or strengthen the beam. So the reduced beam section connection that we'll look at quite a bit in tonight's session and then in the design, that reduces the area of the beam flange and therefore leads in potentially to some extra drift, and so we'll show calculations for that later. Other connections, such as proprietary side plate connection, actually make the beam stiffer at the face of the column, and so create an area of a segment of the beam that is stiffer than the rest of the beam, and that perhaps should be accounted for in the analysis. Certainly, the drift will be lower, and that can be beneficial in allowing perhaps a smaller beam size or a smaller column size. Panel zone shear, as we said, is high shear in the column web in that connection region. Those shear deformations can allow relative rotation of the beam in the column. There are different ways of modeling it, or different ways of, I should say, perhaps modeling in that upper bullet isn't the appropriate term. There are two ways of addressing it. One is to model it explicitly, to include in the model the flexibility of that panel zone. And the other way is not really modeling, although it does have modeling implications. The other way is to use extra beam and column flexibility to represent panel zone shear flexibility. And that is using a center line model. And let's see that in the next couple of slides. Okay, so here is the model with the panel zone. as I mentioned earlier, the beam doesn't actually reach the column center line. So in this model, the beam flexibility stops at the face of the column, and the flexural length is from face of column to face of column. In this modeling technique, the flexural length of the column is from the bottom of the top flange of the upper story to the top of the top flange. Did I say that right? It's between the flanges at each story. So the bottom flange at the upper story and the top flange at the lower story, and that's the flexural length of the column. So far so good, but there is the panel zone to deal with. Within that zone, it's not a rigid square. It is instead a flexible element that represents the flexibility of the column in that region, including both flexural deformations and shear deformations of that panel zone. And the shear deformations can be significant. So this is an accurate way of doing it, and it accounts for the significant sources of flexibility explicitly, but it does require some modeling effort. So how do you model the panel zone? There is some guidance in a NIST document that we'll see at the end in one of the identified resources. This is a reasonable way of doing it, to have a scissor element with a spring, but this is at every single beam to column connection, representing the stiffness that is a function of the column properties and the depth of the beam. A more accurate method that unfortunately requires 8 additional elements is to create a frame at the connection like this, the depth of the beam and the depth of the column, with rigid elements and a rotational spring. And again, that rotational spring accounts for the flexibility that is a function of the column section properties and the depth of the beam. The way that most engineers do it, at least for buildings with reasonable span to depth ratios, the simpler way to do it is to allow the flexural length of the beam to go from center line to center line, and the flexural length of the column to go from beam center line to beam center line, and not to have anything that explicitly models the behavior of that panel zone. So there's a missing source of flexibility, which is the panel zone, but there's extra flexibility in both the beam and the column. And in a number of studies of typical span, moment frame spans, it's been confirmed that this is a reasonable approximation, and that the drift that you get from such a model is reasonably close to the drift you get with a lot more modeling effort. And so, given that our methods of actually predicting seismic drifts are very approximate indeed, the additional effort of modeling the panel zone does not seem warranted for seismic analysis. So this is a sufficiently accurate method of modeling. The error is negligible for typical spans, as I said again, considering that we are taking our knowledge of our loads is very approximate. Our C sub D factor to amplify our displacements is very, very approximate. So the approximation by this modeling method doesn't add to that error. And this requires little modeling effort. So this is recommended for typical buildings. Now let's go into inelastic modeling. As I said, we are assuming that we get plastic hinges at each end of the beam. For purposes of understanding the behavior, I like to use this so-called portal frame method. Now this isn't exactly the portal frame method that many of us studied in school for design. This is a way to isolate one beam column subassemblage from inflection point to inflection point, because in my mind that is the unit, that is the brick that the whole moment frame is built out of. If you understand, design, and proportion this subassemblage correctly, and this is how the building code AISC 341 is written. If you handle this appropriately and then build your frame out of these and proportioning it appropriately as you go, then you get a well-behaved structure. So the key to understanding the moment frame is to understand this beam column connection out to the inflection points. So we isolate that element, blow it up, and say that beam has some shear. How do we know what that shear is? Well, we said we're going to start with the plastic hinge formation at each end of the beam. Now we're looking at a column. We're looking at the right end of the left beam and the left end of the right beam. But the same thing goes. We have two plastic hinges there. We know the value of those plastic hinges. And we've set those inflection points to be at the mid-span of each beam. So we know that this is a triangular moment diagram, at least as far as the seismic load is concerned. And that the shear in the shear at that inflection point, or the shear in the beam throughout the length of the beam, is the value of that moment divided by the moment arm from the inflection point to the plastic hinge location. So now we know the shear in the beam, and statics will tell us that there's a corresponding shear in the column. For simplicity's sake, I am saying that there is no force being delivered at the floor level. That's obviously not true. But this permits us to simplify the problem and design each of the elements. And if you did assume that there was a force at that level, the design is a little more complicated, but by and large you end up with the same sort of proportioning. All right. So there's our shears in the beam, shears in the columns. Now we're looking at members with depth. There's the moment diagram in the beam going all the way to the column center line. Of course, the beam doesn't exist at the column center line, as I've said before. So the beam stops short there. And there's the column moment going all the way to the beam center line. And of course, because of the beam depth, that column moment diagram doesn't reverse instantly. It reverses over the depth of the beam. And so that's the actual column moment diagram and the corresponding shear diagram. And that gives us the panel zone shear. So for each of these subassemblies, I can get essentially design moments in the column, design shears in the column, design shear in the beam, design shear in the beam to column connection in addition to the moment. I can get all of these forces that will help me design the beam to column connection just from this subassemblage. Okay. So we start by analyzing the beam, and we get we assume the plastic hinge forms near the face of the column. We account for things such as the expected strength of material, as we discussed last time, that 50 KSI material doesn't yield exactly at 50 KSI. It probably yields closer to 55 KSI. And then as the plastic hinges go through significant rotation, there's some strain hardening. And that strain hardening might increase the flexural strength 10 or 15%. Very important is locating where the plastic hinge occurs. It does not occur at the center line of the column. It does not occur at the column face. It occurs typically in from the column face about half a beam depth. There are connections that change that a little bit, either through reinforcing the beam or weakening the beam. But you can't change it too much from being near the column face because of the shape of that moment diagram. You can't push it all the way to the inflection point, or you end up with a lot of reinforcement that's required to make sure that that's the weak point. So once we know the value of that flexural plastic hinge moment, we can determine the corresponding seismic shear. There's gravity as well that is considered. And then we can determine the demands on the connection and the demands in the column. So here's a diagram of a span going from column to column. I've shown the column center lines, and I've shown these little dashed regions, these dashed lines. These dashed lines indicate where the plastic hinge is going to form. We'll talk about that in just a moment. So that's our fuse, the plastic hinge that occurs at each end of the beam. And the moment the value of that moment is given the symbol M sub PR, and that's the so-called probable beam moment. Here's the seismic moment diagram. You can see that the moment diagram is not at a maximum where I've drawn this plastic hinge location. This is an old test of a welded connection, welded flanges and welded web beam to column connection. There's no reinforcement and there's no weakening of the beam. And you can see the yielding, well, the yielding is extensive, but if you wanted to assign a location for that plastic hinge, you could assign a location that is half a beam depth away from the column face. And that offset from the column face is now given the symbol S sub H. And as I said, the reduced beam section connection or reinforced connections such as the side plate or bolted flange plate may change this slightly. So the moment at the column face is somewhat greater than the probable moment at the plastic hinge location. And the demand at the center line, which of course is fictitious because the beam doesn't exist there, and that MCL is even larger still. So we're following that moment diagram up to get the seismic moment at the column center line. And the lengths involved are the center to center line length from column to column minus half a column depth at each side will get us the moment at the column face. And then minus this dimension S sub H at each side will get us the distance from plastic hinge to plastic hinge. And that distance from plastic hinge to plastic hinge is given the symbol L sub H. So the value of that probable moment at the plastic hinge location, given in the 2010 seismic provisions, 1.1 times Ry Fy Z. Z is the plastic section modulus. It's going to be reduced for reduced beam section. Fy is the specified minimum. Ry is that factor representing material over strength. So Ry times Fy is the actual expected material yield strength. So for the A992 material that we use quite a bit of for a special moment frame, that Ry Fy is going to be 55 KSI. That factor 1.1 represents strain hardening. Now, in the 2016 provisions, it's slightly different. There was a bit of an inconsistency, not much, but we'll talk about AISE 358, the pre-qualified connection standard. But that standard gives a value of 1.15 for strain hardening, and the seismic provisions gave 1.1. And in 2016, it says just look at AISE 358. So our beams now strain harden a little bit more than they used to, 1.15 instead of 1.1. But essentially the same method. We get the so-called probable moment at the plastic hinge location. We know this length between hinges, and we can solve for the shear. So these are just seismic loads. The moment here, it forms a full plastic hinge, and it forms a full plastic hinge under seismic. Doesn't matter what it was doing under gravity before then. Now that it has these plastic hinges formed, there's a corresponding shear that corresponds to these plastic hinges. Now the beam may still be supporting some gravity load, right? It should be supporting whatever gravity load is on it. That gravity load then will have its own shear delivered to the plastic hinges, but no end moments. So this started as a fixed end beam under gravity, but as we went out to large drifts and developed these drift-induced plastic hinges, the beam is essentially a simple span under gravity. So now the beam is a simple span under gravity. The shear at each end is determinate. At one end, the gravity shear and the seismic shear point in the same direction. At the other end, the seismic shear and the gravity shear are in opposite directions. So for purposes of, say, checking the beam shear, you obviously take the worst case. For a number of other things, we take the worst case too. But remember that at one end of the beam, these are additive, and at the other end of the beam, they subtract. And remember also, when we look at a column, there's the beam on the left and the beam on the right. And so you can always imagine that the beam on the opposite side of the column, if you're looking at the worst case on the left, let's say we're looking at the worst case on the right side of the column. If you look at what's going on the left side of the column, that will be not the worst case. Okay, so here we have that probable moment and the shear due to seismic and gravity, and we can project that moment to the column face. So the moment at the column face is going to be greater than the probable moment by the eccentricity times this total shear. I do like to keep the gravity and seismic shear separate, so I understand and I can play with it when it's adding and when it's working in the opposite direction. So here's the moment at the column face, and we're going to need to check that section at the column face. And then we're going to use the moment at the column center line for some calculations involving the column. That moment at the center line is again the probable moment at the hinge plus the shear times the eccentricity. The only difference with the previous slide is that the eccentricity has now grown from the dimension S of H to S of H plus half a column depth, because we're taking it to the column center line. All right, so now turn our attention to the column. We have some forces based on the beam strength. We also have a requirement for so-called strong column, weak beam proportioning. Again, this is to promote beam yielding over column yielding. Strong column, weak beam analysis, it's a rule of thumb about proportioning. There's no reason you can't look at this instead as the required flexural strength of the column as a load coming from the expected flexural strength of the beam. It's exactly the same sort of calculation. We start with the capacity of the beam and we determine its effects in the column, and we make sure the column has sufficient strength. We also use this capacity from the beam to compute the panel zone shear demands, and again, to make sure that we get flexural yielding of the beam rather than just panel zone yielding. And the column shear is going to affect the panel zone shear demand, and so we use that little subassembly, that Fortle frame subassembly that I showed you before, to calculate those column shears. So the beam capacity gives us the column flexure, the panel zone shear. It requires determining our column zone shear so that we have to determine that shear that corresponds to the formation of the plastic hinges to compute what the net shear is in the panel zone. So there's the column flexure diagram, and that steep reversal of the moment diagram is the panel zone shear. And you can see the panel zone shear, the reversal of that moment diagram essentially corresponds to a shear that's all the way from here to here. So it's the full change of shear in the column that we're talking about, the full change of shear in that column. So whatever shear is occurring in the column above will reduce the net shear that's in the panel zone in the opposite direction. So that is advantageous in design and should always be considered. All right, so again, we're assuming these inflection points at the column mid-height and beam mid-span. uh, and determining the shear and moment diagrams from a free body diagram like this. So here's a little subassembly. In this case, I'm looking at an end column, so it looks like that. There's the shear we got from the beam analysis. That shear, that seismic shear, is constant, so this is just the seismic shear component of it. And then to balance that out, there's the column shear. And again, I'm assuming that that's a constant column shear from inflection point to inflection point, which is a simplification, but is acceptable. Okay, so there's the moment. This is the moment at the column center line. I've drawn it off on the right, but you can imagine it being applied right at the column center line. And we've shown how to derive that by projecting the probable moment to the column center line using the shear times the eccentricity. And here are the column shears from that little portal frame subassembly that we showed before. So here's our centerline moment diagram, and there is the refined moment diagram that gives us a maximum value at the top and bottom flange elevations. There's the required flexural strength. You can think of it as taking that moment, that MCL moment from the beam right at the intersection of center lines, taking half of it up and half of it down, and then subtracting from that the shear in the column times half the beam depth. You can think of it like that. All right, so how do you get that column shear? Well, you have to look at the subassembly, and the subassembly looks slightly different depending on whether we're at the roof location, at the roof elevation, or at a floor elevation, and whether we're at an end bay or an interior bay. So if you look at the upper left corner like this, there's half a beam and half a column, and the shear in the column is going to be multiplied by the height of the column, or half the height of the column, the same way that the shear in the beam is multiplied by half a span of the beam. So the proportioning is such that for statics to work out, the shear in the column is going to be equal to the shear in the beam times the ratio of L over the height of the column from story to story, L being the span of the beam and H sub C being the height of the column. If we look down here, still the end column, now we have two column segments, or rather our moment arm for the column has increased. Instead of being half the column height, it is now one full story height. The moment arm of the shear in the beam remains the same. Therefore, the corresponding shear in the column is going to be less. It's going to be 1/2 of what it was at the roof if these are the same beams and have the same beam shear. So in this case, the column doesn't need to have as much shear compared to the beam as in this case. At this roof elevation, it's the reverse. We have a full span for the moment arm for the beam shear, but half a span for the moment arm for the column shear. And so when we solve for the column shear, we get this, 2 VE L over H sub C. And then our typical case, interior column, not at the roof, it's similar to what we had over here. Okay, so now we'll take a few minutes to talk about Northridge earthquake and moment connections. Okay, so the Northridge earthquake, we had good performance of steel buildings. There was a lot of observation of some damage to beam to column connections. Some of that we thought was damage turned out to be construction defects, but there were still lessons to be learned from that. The typical damage was bottom flange weld fracture or in the adjacent metal. Why did we have this damage? Well, there was high strain at the beam flange to groove weld connection. Nothing we did in our design reduced the demand at the column face, and so that's where it was a maximum, and that's where, as we talked about before, there's a highly restrained condition, that doesn't tend to yield, it tends to rupture. Also, importantly, in the practice of those days, beam webs were bolted rather than welded. And that meant that the full section perhaps participated away from the column face, but near the column face, the bolted joint of the web was not nearly as stiff as the welded joints of the flanges, and the bolted web tended to slip a little bit, and most of the moment and some of the shear had to be transferred in the flanges. The weld access holes that we used in the Northridge days did not relieve the stresses. They did not relieve the restraint in that in that highly restrained condition, and so rupture was the result. Column flange bending without continuity plates and stiffeners. It appeared that there was a lot of column flange bending that perhaps led to some of the fractures. Inadequate stiffening was perhaps a source. Very importantly, the materials we used, the weld material we used was fairly low toughness, and the beam material that we used often had significant overstrength. We tried to proportion grade 50 column material and grade 36 beam material, but the beam material that we used actually turned out basically to be grade 50 as well, and so that proportioning that worked on paper but did nothing in real life. And then the welding techniques that were used, some of them were very poor. A lot of people would say that inspection was poor as well, that the welders got away with doing things that were not allowed by AWS D1.1, and that was a cause for some of the failures, whether they be construction defects or under moderate levels of shaking. This is a diagram showing the flow of flexural forces to the flanges with inadequate participation of the web. To that, I would add a blow up here of the welded bottom flange to beam bottom flange to column flange weld. There is some shear going through here, and that shear results in flexure. When there's tension in the bottom flange, that means the shear is going up, and as some of that shear flows through this welded joint, it causes additional tension right at the bottom of this welded joint. And that's also where the backing occurs. And that backing, if you have a 1-inch flange with a 3/8-inch backing like this that's unfused, it's less like a 1-inch CJP and more like a 1-inch and 3/8-inch flange with a 3/8-inch crack already started in it. And so that's a great place for the crack to propagate from in the bottom flange. So that bending and the presence of that unfused portion of the backing were exacerbating the conditions at the bottom flange. This is I don't know if I'd say typical, but representative observation after the Northridge earthquake. The weld itself looks okay, but it's taken a divot out of the column flange. The backing remained in place. There is what should be a weld tab, but is actually a weld dam that's not allowed by AWS D1.8. So the weld doesn't look very good. It's probably not the right number of passes. It's a low toughness material, and that's where it cracked. Bottom flange is critical for a number of reasons. A couple of them I've mentioned. A third one is that when the welder is performing the welder has to reach through this weld access hole, and where the weld starts and stops, and there have to be starts and stops in this bottom flange weld, that's an opportunity for a defect. Also, at the top flange, there's often a slab that can tend to somewhat reduce the strains in the welded flange. So current practice is a bit different in some very important ways. One is the beam hinge is moved away from the column face. Each connection does it a little differently. We tend to weld the beam web, and so that participates more and takes some of the stress off the flanges. The weld access hole, often we use a weld access hole that's enlarged so that some of that restraint is relieved and you can spread the strain out over a greater length of the flange. We deal with backing differently, and we'll show you in the next couple slides. Very importantly, we use higher toughness materials for welds, and there's better QA and QC measures, better welding techniques, and better inspection. So you can see here there are bolts from beam web to this plate, but this is essentially just a backing plate, and the beam web is CJP welded. We've seen this RBS connection multiple times. It is weakened to move the weak zone away from the column face and to reduce the strain demand at the column face. Of course, the moment diagram goes up, and we still have high moments at the column face, but not the inelastic strains that we expect over here. This is one of the pre-qualified connections, the so-called WOOF-W, welded unreinforced flange welded web. And a couple of things are different. One is you will see DCW, demand critical weld. That's a high toughness requirement for the weld material. It's used in a number of the joints here. What else is different? We have at the top flange, the weld backing remains in place, but gets a little reinforcement here. So instead of being a crack at the edge of that joint, it's essentially a crack that's included within, between the CJP and this reinforcing fillet. At the bottom flange, that's not enough. We ask for the backing to be removed. For this type of connection, the backing's removed, it's back gouged, and it's re-welded with a reinforcing fillet. The weld access hole is improved. The web is welded. So a number of things are subtly different, even if we're just essentially welding a beam to a column. We're doing it with a lot of improvements that give us much better behavior out of that connection. At the column splice, we need to be aware of potentially high stresses, and so we taper width and thickness at transitions. Weld tabs are removed, and we grind. Backing can remain in place at these butt joints. The T-joints are much harder on the material. The butt joints are not as sensitive. And there's no supplemental fillet required. In the 2016 seismic provision, the partial joint penetration weld is allowed under a number of limitations, and it has to be 85% or greater than the effective throat. So partial joint penetration weld with high toughness that fuses most of the joint seems to be good enough to allow this the column splice to function quite well. All right. When we design these beam to column connections, we're transferring moment from the beam to the column. There are a number of different limit states that we check. There's the potential for weld rupture at the flange, column flange bending, web local yielding, top or bottom, web crippling where it's in compression. Panel zone shear can also occur. We have to check all of these things in our beam to column connections. I'm not showing the web compression buckling. That would be for a cantilever. This is more for a frame. And for panel zone yielding, the participation of the beam on the other side is also important. And of course, we have to design that beam shear connection. If we come up short on some of these limit states, we might add a continuity plate, or we might add a doubler plate. Okay, so for checking these, we calculate the moment at the column face, and we turn it into a point load. That point load is the moment at the face divided by this depth between flanges, There's a refinement in the 2016 provisions that allows us to take 85% of that if we have a welded web. So we assume 15% might go to the welded web. If we come up short in any of these, we need to design a continuity plate for the difference in capacity. There are also some triggers for continuity plates special to moment frames. If the column flange thickness isn't thick enough, according to this test, it's essentially a stiffness test, we add a continuity plate. And then there's this check that's in the 2010 provisions, but is eliminated in 2016. It's essentially a concentrated load checking the column flange for flange local bending with a very high load. And it's already taken care of, so we've dropped it from the seismic provisions. Continuity plates, there's a minimum thickness. If it's a one-sided connection, half the thickness of the thicker beam flange. If it's a two-sided connection, in the 2010 provisions, it should be the full thickness of the thicker flange. In the 2016 provisions, down to 3/4. And there are very large clips that are required by AWSD 1.8, essentially to limit the welding to the flat part of the web. All right, so we do a similar thing with the moments at the column face to check the panel zone yielding, but as I said before, we subtract out that column shear, and that gives us the panel zone shear. The 85% does not come into it here. And then we turn to AISC 360, and and we get different strengths for panel zone yielding. You have to check to see if your axial force is very high, what your panel zone deformation, whether your panel zone deformations have been accounted for, which isn't really an important question for the seismic analysis because we're deriving our forces from the capacity of the beam. Generally, I just like to use the web because that second term over here, this flange bending term, that involves a lot of deformation to get out to mobilize that. Then we have the strong column, weak beam requirement. Ratio of 1 makes a story mechanism unlikely. Ratio of 2 makes a column yielding unlikely. And here's our capacity of the column. This last term is the effect of the column shear, which we can take as being additive. And this is the demand coming from the beam. And again, that plastic hinge has a slightly different flexural value in 2016. So the difference, that extra term, the shear times half the beam depth, is how you get to the moment at the column center line. Okay, we're going to deal with this quite a bit in the design example. If you have a design and you found that you need continuity plates and doubler plates, you can look at this subassemblage as a little spring. Shear in the column leads to some relative beam to column rotation in this subassembly. Now you could redesign it with a heavier column and a lighter beam and get the same stiffness in the subassembly. So your overall frame won't know the difference, but you'll have a heavier column and a lighter beam, and maybe you won't need the continuity plates and doubler plates. So I'm giving you some equations here. I don't want to derive them in this talk, but essentially we're saying the flexibility is from two sources. There's the flexibility of the column and the flexibility of the beam, and these are additive. And if you want, after your redesign, to have the same flexibility, you can solve, if you've picked a column, you can solve for a beam stiffness. So here we go. H is the story height of the column, L is the beam span, NC is the number of columns, so it would be 2 here and 2 beams here, but it could be different in different areas. And you solve for the moment of inertia required of the beam based on your redesigned column and your original column and original beam. And if you're not at the drift limit, you can take advantage of that as well and say, well, I can solve for the beam that I need rather than the beam that's exactly the same, leads to the same stiffness as I had before. So let's take a few minutes to go through the construction of a moment connection. Here's the beam in place. The flanges have been prepped. You can see the weld access holes. This is slightly different. This is slightly out of date because now we would expect that web to be CJP welded to the column flange for most connections as well. Okay, so the backing bar has been put in place with a few tack welds. These tack welds are then incorporated into the final weld. That steel backing is 3/8 of an inch. Then the weld tab has been added, so that creates a groove. So at least at the end, the starting and stopping can take place outside of the final joint. But as I said before, reaching through the web, you have to start and stop at the bottom flange. First pass goes in through the weld access hole, and it keeps building up until it's finally done. Top flange also has a weld access hole. It's not for the welder to reach through, but it is the steel backing does go through. You can see the weld tab at the top here. And then the CJP weld is done pass by pass. There's no starting and stopping within the final joint here. And then here at the bottom flange, the backing has been removed, the weld tabs have been removed, and it's been ground reasonably smooth to get rid of discontinuities in that area. And then this is a different connection with a cover plate. There is inspection. This is ultrasonic testing that looks for flaws, inclusions, discontinuities in that final welded joint. All right, switching gears a little bit. For ordinary moment frames, we just have a requirement to develop the beam strength, use notch-tough materials, and some special detailing at the joints. For special and intermediate moment frames, we have to use a pre-qualified connection or one that's qualified by testing up to a defined rotation. So that brings us to our pre-qualified connections. So if we use if we use qualification testing, we have to match pretty closely what we're going to use in the building. If we use pre-qualification, well, a panel of experts has looked at the existing testing and decided what buildings can be built, or how much this testing can be extrapolated for application to buildings. And so there are limits on what you can do with these pre-qualified connections without further testing. And this is in a published standard, AISE 358, which we call the pre-qualified connection standard. And there's a special AISE panel that has gone through multiple connections and defined the design methods, the limits of applicability, and other requirements. I'm going to go through most of those right now. The reduced beam section connection weakens the beam. Face of the column has relatively less demand. It's still greater moment, but the demand capacity ratio should be lower there. And we use capacity design to proportion everything else so that we get most of our yielding in that reduced section. And there's a potential reduction in stiffness and potentially in stability. Here's a photograph of an RBS connection. Bolted end plate, again moving the connection away from the column face. The end plate is stronger than the end plate connection is stronger than the beam. And we do capacity design starting with the beam flexural strength and following from there. Bolted flange plate, the beam is the fuse, the flange plates transfer the moment, not the beam web in this case. And there are all sorts of bolt limit states to check. We've talked a little bit about this welded, unreinforced welded flange. It looks a lot like the pre-Northridge connection, but they're improved materials, better toughness, limited tensile strength, improved welding details, including the weld access hole and backing details, removal of weld tabs, improved QA, QC. Kaiser bolted bracket is a proprietary connection. It's very similar to the bolted flange plate. It could be welded to the beam or bolted to the beam. It's always bolted to the column. And the beam is, of course, the plastic hinge, the fuse. And we use the forces from the beam to design the rest of the connection and the column. The Connect Cell connection by Connextech is a two-way connection, another proprietary system. Bolted collars on a 16-inch concrete-filled box column. If required, if the beam is large enough, they'll do an RBS in it to meet strong column, weak beam. And the beam is expected to yield, and we'll do a capacity design. And the interesting thing about this one, or one of the interesting things, is that it's bidirectional, and so it needs examination of both axes. I will say that I don't have in this presentation, but in the 2016 provisions, we have the side plate connection, the Simpson strong frame, and the double T connection, which is not the double tree connection from Hilton, but the double T, which is similar to the bolted, bolted flange plate. AISC 341 allows pre-qualified connections and defines what pre-qualification is. It does not say you have to use AISC 358. However, the AISC panel definitely is an appropriate panel for pre-qualification. There are other entities that conform to the requirements of pre-qualification. Committees, ICC Evaluation Services puts together a panel, and they've looked at different connections, slotted web, and there's also the free flange connection that's been tested extensively, welded haunch. All right, I have just a few minutes here. I want to touch on a couple of additional topics. Stability bracing is required. We're bracing at the column, bracing near the plastic hinge location, not within it, but just adjacent to it, and bracing at a defined spacing. The seismic provisions say if you have an adequate composite deck, you can get rid of that first brace adjacent to the plastic hinge. Diagram of stability bracing. Protected zones, we don't allow certain attachment shot pins, low toughness welds, and the like in these regions where we expect the plastic hinge to occur. Typically, it's about a beam depth in from the column face. It's the protected zone. Our special weld toughness requirements, these demand critical welds occur at the beam to column connections, at the column splices, and column bases. Okay, so in summary then, moment frames provide inelastic drift through beam hinging. Proportioning of moment frames favors beam hinging and increases inelastic drift capacity. And we have to be careful of our highly restrained welded joints at beam to column connections. To protect them, they require attention to detail to allow yielding to occur somewhere in the beam before rupture of these joints. All right, so with that, I'll remind you that we have a couple weeks off, and then we come to seismic design of braced frames.
Okay, thank you, Raphael. We are going to jump into the Q&A here, but first we're going to do a couple polling questions before we answer some questions from the audience. Okay, if I can just find these slides. Sorry about that. Here's our first polling question. True or false, continuity plates are used to reinforce the column for panel zone shear? True or false, continuity plates are used to reinforce the column for panel zone shear? You can go ahead and select your answers. Looks like most of you are familiar with this, but you can click on one of those radio buttons and submit your answer. We'll give everyone a few more seconds here if you want to join us. All right, so true or false, continuity plates are used to reinforce the column for panel zone shear? Raphael, what do you think? Looks like we have.
So I'm. Yeah,
Sorry,
it's a tie here, so I can't go with the audience. Yeah, and I will take that as a lesson to me. We'll focus on it a bit in the design example. Continuity plates are for local limit states of flange bending, web local yielding, and web crippling. So they're a way for that concentrated flange force to find its way into the web. If the web itself can't resist it in panel zone shear, though, that's when you need a doubler plate. So that's the answer is false. The continuity plates don't help with panel zone shear. It's the doubler plate that you would put as a reinforcement for panel zone shear.
Okay. All right. Let's do one more polling question, and then we'll get into the Q&A. For our next question, choose one answer to this one only. So for the strong column weak beam ratio should be greater than 1.0 so that A, story mechanism becomes unlikely, B, column flexural yielding is prevented, C, panel zone yielding is prevented, D, both A and B are correct, E, A, B, and C are all correct, or F, none of the above. Again, the strong column weak beam ratio should be greater than 1.0 so that a story mechanism becomes unlikely, B, column flexural yielding is prevented, C, panel zone yielding is prevented, D, both A and B are correct, E, A, B, and C are correct, or F, none of the above. Got a few more seconds if you want to submit an answer before I close this poll. All right. We're getting some interesting results on this one as well, Raphael. Let me go ahead and close that poll. So it looks like most people chose both A and B, and a handful said A, B, and C, and a handful said just A. What would you like to say is the right answer?
Well, I would say the most correct answer is A, that the reason we have a strong column weak beam requirement to be greater than 1 is to address story mechanisms. We did say in, I'm not sure which slide, early on that the strong column weak beam ratio greater than 2 makes the flexural yielding of the column less likely. But it has to be a lot greater than 1 to address column flexural yielding. Of course, having a strong column weak beam ratio greater than 1 is better than having a strong column weak beam ratio less than 1, and will tend to, you know, the greater you make that ratio, the less the column flexural yielding will be. And I guess the same is true of the panel zone. The heavier you make the column, the less likely it is that the panel zone will have yielding. But neither of those things is really directly addressed. It's really the story mechanism that is addressed by the strong column weak beam ratio of 1 or greater.
Okay. All right. Let's jump into a few questions here before we wrap things up. A couple of questions on column bases. Can we allow plastic hinge in the base plate instead of the column end? And if not, why not?
So the answer is yes. We can allow plastic hinging in the column in the base plate rather than the column. We'll actually look at that in some detail in the design example. But there are a couple of considerations there. One is it's tricky. That column base plate has to have enough strength to resist some defined loads from the code. And also, the compression in the column tends to increase the flexural strength at the base. So that base plate is being held down by anchor rods, but it's also being held down by the gravity loads in the column. We size the anchor rods for the worst case, thinking that perhaps there's no live load on that column and only 90% of the dead load, and then we take the vertical component of the earthquake going up. But under expected levels of compression, there will be less tension in those anchor rods, so those anchor rods will effectively be delivering more force and holding that base plate base plate down more than one considers in the design of the base plate. So to summarize, then, the compression in the column is another source of overstrength of the base plate and has to be overcome before the base plate will yield.
Okay, I'm going to go to slide 33. Okay, here's the question. The flexural length is assuming the beam spans into the flange of the column. What if the beam frames into the web of the column?
Yeah, so if the beam frames into the web of the column, you can take a similar approach. The panel zone shear, though, is the shear deformation in that panel zone is likely to be pretty small for the column oriented in its weak axis, because instead of the web you have two flanges, and the flanges tend to be quite a bit heavier than the web, and of course there are two of them. So I think the centerline modeling that we discussed is reasonably calibrated for a column oriented in the strong axis, and might be more flexible than it needs to be for a column oriented in the weak axis.
Okay, I'll take us next to 35. In discussing these panel zone models, just for clarification, is this model simply a column/beam centerline model for analysis then?
No. So for analysis, you would need these additional nodes, as shown here, around the beam to column intersection. And there's just a little bit more detail in that NIST document I showed you on slide 103, which is also a free download. Seismic Design of Steel Special Moment Frames by Ron Hamburger, Helmut Krauwinkler, James Malley, and Scott Aiden. So there's a little bit more guidance on modeling the panel zone in that document. But I would encourage designers to consider using the centerline model instead for typical practice.
Okay.
I would say don't model the panel zone unless you have a very good reason to do so.
Okay, and then here's a follow-up question on the question regarding framing into the weak or into the web of the column. Are there any pre-qualified special moment frame connections for framing into the weak axis?
So the pre-qualified connections that I went through, let's start with the ConnexTech connection. So that one is a special square column, concrete filled. There is no weak axis. All of the other ones are pre-qualified for connection to the major axis of the column, or to box columns, or to cruciform columns built out of wide flanges. They are not pre-qualified for connections to the weak axis. Now, connections to the weak axis have been done for years. I'm not aware of any observations of problems with those connections in the Northridge earthquake. All of the problems that I'm aware of have been columns in the strong axis and those T-joints of the beam flange to the column flange. There has been testing of some weak axis connections, I know, with the slotted web connection. I'm not aware of others, though.
Okay. Here's a question, another question about panel zone shear. Can we ignore column panel zone shear check per AISC 360 if we use the centerline model in design?
Okay, so let's be very clear about that. You have to check the panel zone shear regardless of which way you analyze, whether you use the panel zone model as being shown on the screen now or use the centerline model. Regardless, you will have panel zone shear, and you have to analyze it. You have to calculate it essentially the way that I've presented in today's class and make sure that you have sufficient web strength.
Okay. And then just for clarification, I'm going to move to 70 here. Can you clarify what M sub PC is?
So NPC star is part of that strong column weak beam requirement in AISE 341 in chapter E3. So that's the column moment capacity part of the strong column weak beam. That's a strong column weak beam ratio. So this is the, let's see,
You still there, Raphael?
yeah, sorry, I was looking for where we, which slide we have that ratio on. It's on slide 69. Yeah, so there's the strong column weak beam ratio, NPC star and MPB star. It's the moment capacity of the columns, say the column above and below the connection, compared to the moment capacity of the beam left and right of the connection. And the MPC star is the plastic section modulus of the column times Fy minus how much we're using in axial, and that would be in using the same load combination. So usually this is the overstrength seismic load divided by the area of the column. And then if you want to take full advantage, which a lot of engineers don't do, but you can also account for this shear in the column times half the beam depth, essentially to project the strength from the top flange of the beam to the beam center line.
Okay, thank you, and we are out of time, and have a good night.